Good day, we are the Group 7 of Class 8N, and our project is about solving traffic problem using MATLAB. In this video, we use system of linear equations to determine the number of vehicles that should be allowed to route in 4, 5, and 6 one-way street in order to keep the traffic flowing. The system of equations used in the model were solved analytically using the method reduced row echelon form. But before that, let me do a short introduction first. In mathematics and civil engineering, traffic flow is the study of interactions between vehicles, drivers, and infrastructures, including highways, signage, and traffic control devices, with the aim of understanding and developing an optimal road network with efficient movement of traffic and minimal traffic congestion problems. The purpose of the project is to apply a system of linear equations to traffic flow for a network of 4, 5, and 6 one-way streets. It also aims to determine the number of vehicles that should be allowed to route the 3 given one-way streets under study in the model in order to reduce traffic congestion. Let's start.
For part 2, we have the traffic problems. We have 3 problems. Problem 1 is 5 algebraic equations, problem 2 is 6 algebraic equations, and problem 3 has 4 algebraic equations. This is the illustration for problem 1, and it says here that the traffic control center has installed electronic sensors that count the numbers of vehicles passing through the 6 streets that lead into and out of downtown area. The arrows represent the one-way direction of each street, and the numbers shown below are the numbers of vehicles per hour that pass through the streets. It leads to a system of 5 linear equations that model the traffic flow. These are the algebraic equations per intersection. We have 5 intersections, so we have 5 different algebraic equations as well. To find the equations per intersections, the variables or the values going into the intersection are equal to those who are going out, and we have to equate the given value. From the algebraic equations that we have, we can now transform them into an augmented matrix that we need to input in our MATLAB to get our answers, the missing values. We have here the A values of our augmented matrix, which came from the constant of x's, and the V, the values. This is how we put our augmented matrix. First, we have to put the A values. Then in line 6, we put inside a parenthesis the column of B. Then, we have to equal it to the value of B. And all we have to do is run the system and we can get the values we are looking for. This is the screenshot of what we did in the video. We can see the augmented matrix we have and how the MATLAB system solves our problems using reduced row echelon form, or the RREF. This is the system equations of problem 1. The first part is the answer we can get from the Gauss-Jordan method. We can see here that x6 is free, which means the problem is dependable based on the value of x6. Well, we use the RREF method. In the RREF method, which assumes that the value of x6 is 0, that is why we can get the value of x1 to x6. x1 is 75, x2 is 575, x3 is 275, x4 is 175, x5 is 375, and x6 is 0 vehicles per hour. Problem number 2. A traffic engineer wants to know whether measurements of a traffic flow entering and leaving a road network are sufficient to predict the traffic flow on each street in the network, depicted as F1 to F7. The numbers in the figure above represent the measured traffic flow in vehicles per hour. Also includes the illustration we have to solve. These are the linear algebraic equations for our 6 intersections. In finding the equation for intersections, same to what I discussed earlier, the variables and values going in are equal to going out. Using algebraic equations, we can form our augmented matrix, and this is our augmented matrix for problem 2. This augmented matrix is what we are going to input in our MATLAB system. The procedure is same in problem 1. We can get our answers, the value of F1 to F7 when we put our augmented matrix and run the system. This is the screenshot from the video. We can see here how MATLAB solves our equations using the RREF method. This is the system of equations. The first part is the answer we can get using the Gauss-Jordan method. And we can see that the two variables, F6 and F7, are free. This means that this is a dependent problem. The values of vehicles per hour we can get depends on the value of F6 and F7. But using the RREF method, it assumes that the value of F6 and F7 is 0. That is why we can get the values of F1 to F5, which is F1 is equals to 100, F2 is 0, F3 is 0, F4 is 200, F5 is 600 vehicles per hour, and F6 and F7 are 0 vehicles per hour. Let us move to problem 3. This is the illustration, and it says here that the network in the figure shows the traffic flow in vehicles per hour over several one-way streets in the downtown area of a certain city during a typical lunchtime. Cars are not allowed to park on the streets, which means that the total flow of cars into an intersection must equal to the total flow of cars out of an intersection. Determine the general flow pattern of the network. Solve the system of equations. In this problem, we have 4 intersections. That's why we have 4 linear algebraic equations. In getting the equations, look at the illustration. The variables and values going inside are equal to those who go outside of the intersection. From our linear algebraic equations, we can formulate our augmented matrix that we need to input in our MATLAB system. Same from problems 2 and 3, we just need to input our augmented matrix to the code we have and run the system to solve for it. This is the screenshot from our MATLAB. We can see here our augmented matrix in the process of solving our matrix system. This is the system of equations in problem 3. The first part is what we can get in using the Gauss-Jordan method. As we can see, the value of x4 and x5 are free, which means this problem is dependable because we do not have the exact values of x4 and x5. That is why we use the RREF method. It assumes that free variable is equal to 0. That is why we got answers. x1 is equals to 1,500 vehicles per hour, x2 is equals to 2,500 vehicles per hour, x3 is equals to 1,400 vehicles per hour, and x4 and xy, the free values are 0.
In conclusion, we use a system of linear equations to determine the number of vehicles that should be allowed to route a couple of one-way streets in order to keep flowing. By using linear equations, can solve traffic flow and resolve traffic's problem. A traffic engineer can solve this kind of problem involving in designing traffic, control device installations and modifications, including traffic signals, signs, and pavement markings by using different systems of equation for analysis in solving traffics. The system of equation used in model were solved analytically using the method of reduced row echelon from RREF. This system is the model can solve the problems, but we truly suggest by solving traffic flows, it is not answering only one system. It can be more systems are able to answer traffic problems. It is, in this case, we use system of equations was reduced row echelon form or RREF system. Thank you.